This is Applied Calculus, Lesson 1-3, Linear and Quadratic Functions. Our textbook starts this section off by discussing the definition for slope of a line. If you have 2 points, x1, y1, and x2, y2, such that these 2 points have different x values, then the slope of the line these points lie on can be calculated using the formula m equals y2 minus y1 over x2 minus x1. Another way to express this is delta y over delta x, and this is how we calculate the rise over run for slope of a line. Table 1 gives us geometric interpretations for slope. If a slope is positive, then it rises from left to right. If it is negative, then it descends from left to right. If it is horizontal, it does not rise or run. And if it is vertical, it has an undefined slope, where undefined slopes occur when we have 0 in the denominator. Zero slope is the result of 0 in the numerator as long as the denominator is not 0. Table 2 addresses different forms for linear equations. We have the standard form, the slope-intercept, point-slope form, the formula for horizontal and vertical lines. So the definition of a linear function: if we have m and b that are real numbers such that m is not equal to 0, then the function f of x equals mx plus b is a linear function, and this linear function can also be called a linear equation if you replace f of x with y. And we said this in previous lessons, that f of x is a function name, but it holds the value for the y variable. Addressing this note here that m is not equal to 0, if m were equal to 0, we would get f of x is equal to b, and this is known as a constant function. Because b is a constant and there's no change in the output for different x values, and this gives us a horizontal line. So in this example, we're asked to graph the linear equation 3x minus 4y equals 12. We're going to do this with intercept graphing. We'll find the x and y intercepts. So you set x equal to 0 and solve for y, and then you set y equal to 0 and solve for x, and that will give us 2 points on a line that we can connect. So we see that when we make x 0, we have negative 4y equals 12. We get y is negative 3. And if we make y 0, we get 3x equals 12. We would get x is 4. And if we plot these points, 0, 3, and 4, 0, we can connect them. And part B asks that we rewrite this linear function in slope-intercept form. So we'll take 3x minus 4y equal to 12, isolate the y variable, and now we can replace the y with f of x equals 3/4 x minus 3. So that's your answer to part B. And then part C says solve the inequality f of x greater than or equal to 0. So we'll take 3/4 x minus 3 and set it greater than or equal to 0. And we solve this pretty much the same way as we would any equation. Multiply by the reciprocal on both sides to cancel out the fraction. And part C, the answer is that f of x is greater than 0 when x is greater than or equal to 4. And we can see that when x is 4 or larger, the y values are 0 or larger. Here we have interval notation. Interval notation is another way to address which parts of the domain of a function um, are applicable to a problem. And we see that they give us the inequality notation equivalent. So notice that when the inequality uses an equal bar, our interval notation uses square brackets. And when the inequality is missing the equal bar, our interval notation uses a parenthesis. So square brackets include the endpoints of an interval. Parentheses say up to, but not including the endpoint of an interval. And all of the examples below give you mixed brackets with parentheses and square brackets. Another note is that infinity can never have a square bracket because infinity is not a number, it is a concept. You can never contain infinity in a square bracket. So here we are given the definition for a quadratic function. If a, b, and c are real numbers such that a is not equal to 0, then the function f of x equals ax squared plus bx plus c is the standard form for a quadratic function, and we'll have a graph that is a parabola. Just to emphasize, a is not equal to 0 still gives us a quadratic function or a graph that is a parabola. It is okay if b and c are 0 and those terms cancel out. However, if a were equal to 0, the quadratic term would cancel and we would be left with either a linear or a constant function. So it is necessary that a not be equal to 0 if we are talking about a quadratic. The domain of a quadratic function is the set of all real numbers. We see that we can choose any x value from negative infinity to positive infinity. So the domain is x, which belongs to the set from negative infinity to positive infinity, or x, which belongs to the set of real numbers. The range will go from the minimum value of the parabola and extend to positive infinity, or from the maximum value of the parabola from negative infinity. So I can write the range of this first graph as -4 to infinity. It includes -4, but does not include infinity. This second graph has a range, and I'll say y belongs to the set from 2 to infinity. And this third graph has a range, y belongs to the set. We're starting from negative infinity and going up to 4. And notice that the vertex point is included, so we use a square bracket for the vertex point. So we're going to plot this parabola. It says find the x and y intercepts and plot them along with other solutions. We're going to sketch the graph using 5 points. So to find the x and y intercepts, we set x equal to 0 and solve, and then set y equal to 0 and solve. So the y-intercept is when x is 0. If we plug in 0 for x, we get 3. And the x-intercept is when y is 0. And we're going to get 2 solutions this time. So we change f of x to be equal to 0. I'm going to divide each term by -1, so I get the lead coefficient to be positive. And now we can factor this. And we get x equals 3 and x equals -1. And we will put those values into the points up here, 3, 0, and -1, 0. So far we have 3 points. We can start to plot them, 0, 3, 3, 0, and -1, 0. So we want to choose 2 more points to satisfy the 5 points to plot this graph. So I'll choose 1 and 2 since they're in between those known points. So f of 1, plug in 1 for everywhere that you see x, and you get -1 plus 2 plus 3, which is 4. So that is the ordered pair 1, 4. And then we can plug in 2. So we'll evaluate f of 2 and get 3. So that is the ordered pair 2, 3. And we can connect these points and see the graph of our parabola. And you can choose as many additional points as you'd like. We can choose -2, -3, -4, plug them into the function, get the corresponding y coordinates, and plot them on the graph. Next, we will discuss the vertex form of a quadratic function. On the previous slide, we saw that this is standard form. So that's f of x equals ax squared plus bx plus c. And now we would like to get vertex form. And the benefit here is the h and the k values will give us the location of the vertex. And what we're going to use is completing the square. The method of completing the square allows us to rewrite this quadratic function into vertex form. So you'll see the first step taken is to factor out the lead coefficient. When completing the square, we need to work with an x squared term that has a coefficient of +1. Once you have that, you can then say what constant do I need to add to this trinomial to make it a perfect square trinomial. And to do that, you take the middle term, which is -8, and you take half of that and square it. So half of -8 is -4, and when you square -4, you get +16. Now we've changed our equation by adding this constant. So we have to say this -2 times this +16 is -32. That is how we changed our equation. So to balance our equation, we need to do the opposite of that. And that's why there is a +32. This will balance it out. So you combine that 32 with the -24, and you're left with 8. And we see that our h value is 4, our k value is 8. So we know that the vertex of this parabola is at 4, 8. So one of the oversights is sometimes students don't pay attention to this negative that is in the formula. So if this were to say x plus 4 in the parentheses, that would mean our h value is -4. So it needs to be x minus 4 to indicate that our h value is +4. And similarly, if this said -8 out here, our k value would be -8. And this goes along with what we've said earlier with translations, that the value inside of the parentheses gives us the opposite result than we expect, and the value outside the parentheses gives us the result we do expect. So the +8 will be interpreted as a +8, the -4 would be interpreted as a +4 because it's inside parentheses. So here's a list of properties for quadratic functions and their graphs. So you can rewrite standard form into vertex form. That allows us to easily identify the location of the vertex. And if the a value out front is positive, it opens up. A is greater than 0 means a is positive. And if you look at the parabola, it's kind of like a smiley face. So when it's positive, we smile. But when a is less than 0, it is negative. And when we're negative, we frown. So the parabola opens downward. So we can get the location of the vertex. The x value of that vertex is the axis of symmetry. Notice that the parabola is balanced around that axis. And if the a value is greater than 0, then we have a minimum. If the a value is less than 0, meaning the parabola opens down, then we have a maximum. That is what rule 4 is indicating. And the domain is always all real numbers, but the range, we would look at the way it's opening from a minimum to positive infinity, or from negative infinity to the maximum. We would write our range. And we can express the graph of a parabola in vertex form using translations. So example 4 asks us to demonstrate each of these properties from the quadratic equation being in standard form. We will rewrite it in vertex form, and we will graph it and identify max, min, and range. So we start by taking f of x. We want to factor out that 0.5 from any x terms. So we have 0.5 x squared minus 12. There will be a third term that will complete the square, and the 21 will be outside the parentheses. To double check that we factored correctly, if I distribute this 0.5 through here, do I get back the numbers that were given in the beginning? And we say yes, 0.5x squared, and 0.5 times negative 12 gives us negative 6. So now we can complete the square. We will take half of this, there should be an x here, we will take half of this linear term and square it. So half of negative 12, and we square it, we get half of negative 12 is negative 6. Negative 6 times itself is positive 36. That is what completes the square, but really 0.5 times 36 is plus 18. We've changed our function by adding 18. We have to balance it by now subtracting 18. So f of x is equal to 0.5. We complete the square because it's easy to factor. It's going to be x minus the square root of 36, x minus 6. We put all of that in parentheses and square it. And then we combine these constants out here, and we get a plus 3. And this is our vertex form. We now see that we have an h value of 6 and a k value of 3. So our vertex is at 6, 3. And because our a value is positive, it opens up. So if I find 6, 3 and plot a point there, and I know that it opens up, I'm not getting exact points because we're just answering the questions they've provided for us. So here's part A, vertex form. Find the vertex and the maximum or minimum. Well, we see that this is a minimum of y equal to 3. State the range. So we can say that the range is y, which belongs to the set of closed bracket 3 to infinity with a parenthesis. C says describe how the function f can be obtained from the graph of h of x equals x squared. So this is the parent graph. And we would say that f of x is equal to 0.5 times h of x. And then we would shift 6 units to the right. So translated 6 units right, and then 3 units up. And D says sketch a graph of the function in a rectangular coordinate system. If we wanted to add some precision, we can just choose some x values to plug in. So if I plugged in 4, 4 minus 6 is negative 2. Negative 2 squared is 4. 0.5 times 4 is 2. 2 plus 3 is 5. So we would get 4, 5. And then I would use the symmetry property to reflect that point. And we see my graph wasn't that bad. I just have to adjust this one branch. And that gives me a better likeness of this parabola. Example 5 is a linear application. So we're going to use some business application with the mathematics we're reviewing. It states at a price of $9 per box of oranges, the supply is 320,000 boxes and the demand is 200,000 boxes. If the price is at $8.50 per box, then supply is 270,000 boxes and demand is 300,000 boxes. So part A says find a price supply equation. So they want to know what's the price that is generated by the supply. That means price will be the output, supply will be the input, and we can say S of x, which is our supply equation or our supply function. It has two ordered pairs. So we have at $9, the supply is 320,000. So we'll say 320 and 9, where x is in thousands. And then our second point was that when the price is at $8.50, supply is 270,000. So our second point will be 270 and 8.5. So this will allow us to create a price supply equation. So we can find the slope, 9 minus 850 over 320 minus 270. And that gives us 0.5 over 50. And we can simplify this fraction as 0.01, that is 0.5 divided by 50, and that is our slope. So we have y equals 0.01x plus b. And what we do now is choose any one of your points and plug it in for x and y. So 9 is equal to 0.01 times 320 plus b. And if we do 0.01 times 320, we get 3.2 plus b. And if we subtract 3.2 from 9, we get that b is 5.8. So our supply function is 0.01x plus 5.8. So now part B wants us to do our demand equation. And we're going to let d of x be our demand function. And again, they want P to be the output for input x. So when 9 is the output, the demand is 200. That's the input. So we have 200 comma 9. And when 850 is the output, 300 is the input. We have 300 comma 8.5. Again, x is measured in thousands of boxes. We've established that for this problem. So the slope will be 9 minus 850 over 200 minus 300. This gives us 0.5 in the numerator and negative 100 in the denominator. So the slope is negative 0.005. We can now say the demand function is negative 0.005x plus b. We can choose any one of our known points, plug in the output of 9, multiply it by the input of 200 plus b. So 9 is equal to negative 1 plus b, or 10 is equal to b, and our demand function negative 0.005x plus 10. So we can set these two equations equal now to find out where they will intersect. So we can set these two equations equal now, find out where they're going to intersect. And let's subtract 5.8 from both sides. That gives us 4.2. And x is equal to 280. And if we plug that 280 into either of these equations, we can find the price. And we get a price of $8.60. Knowing this information helps us to set up a reasonable graphing plane for our equations. So for part C, it says graph the price supply and price demand equations in the same coordinate system and find their points of intersection. So we'll do this in a graphing calculator. We'll hit y equals. We'll put in the supply equation. And then the demand equation. And we'll hit graph. And it looks like parallel lines because these slopes are so small. So that's where knowing the answer in advance helps us. I'm going to go to Window. My x is going to go up to 280. So I'm going to set an x minimum of 0 and count up to 400. And I'll say count by 25s. And my y minimum I'll put at 0. And I'll go up to, let's say, $10. And I'll count by ones. And when I hit graph, now this equation is going to make more sense to me because the scale has been adjusted. And we can hit trace and trace the line until we get to the approximate intersection. And we can see that the x is about 280 and the y is about 860 just from tracing. So that was just tracing it on the calculator. Or notice above trace, there's a blue menu option called calc. So if we hit the second and then calc, intersect is option 5, and we can hit enter, enter, and a third time, and it tells me it intersects at x equals 280 and y equals 860, which is the answer we got. But here is the graph that represents this linear system of equations for our supply and demand curves. So here's example 6. It is a quadratic application problem. So this is a continuation from section 1.1. We were given these price demand functions and revenue functions, and the domain was from 1 to 15, including the endpoints. Part A asks that we find the value of x to the nearest 1,000 cameras that will generate the max revenue. And they want us to do this algebraically using the completing the square technique. So we'll start by writing our revenue function. We'll distribute this x through the parenthesis, negative 5x squared plus 94.8x. We'll go back to our calculator. Let's clear everything out. And we're going to factor out that negative 5. So we have a lead coefficient of positive 1. And when we divide 94.8 by negative 5, we get negative 18.96 x. Then we are going to complete the square. So to complete the square, we take 1/2 of negative 18.96. And that gives us negative 9.48. And then we square negative 9.48. And that gives us 89.9. So the value that completes the square is 89.9, but that's really being multiplied by negative 5. 89.9 times negative 5. So that's negative 449.5. And we need to balance that by taking a positive 449.5. Now we can write our R of x in vertex form. X minus 9.48 in parentheses squared plus 449.5. That means our vertex is at 9.48, comma 449.5. So part A is asking for thousands of dollars and thousands of cameras, but the instructions in the beginning were saying millions of cameras and millions of dollars. This is the intent. This down here was a typo. I referred to the answer key to verify that. So if we multiply this by millions, we have 9,480,000 cameras. Generate a revenue of $449,500,000. Part B, what is the wholesale price per camera to the nearest dollar that generates this maximum revenue? So if we take the 9.48 and plug it into the price demand function, we get P of 9.48 equals 94.8 minus 5 times 9.48. And that's $47.40 per camera. Part C says graph the revenue function using an appropriate viewing window. And again, because we see that this is going to go up to a large number on the y-axis and a smaller number on the x-axis, we can adjust the window. So if we put the revenue function in, negative 5x squared plus 94.8x. And if we hit graph, we see this is not giving us a clear graph. We're going to go to our window button. The x-axis is going to go from 0 to 10, and that will give us the maximum. So let's go past 10 to see it falling from the maximum. So we'll go from 0 to 20, and we'll count by ones. And the y-axis will go from 0 to 500, and we can count by 25. Now when we hit graph, you see that the maximum is occurring at the vertex, and the instructions tell us to graph it with the appropriate viewing window. We've done that. Part D says find the value of x to the nearest thousands, and they want us to use the maximum command. So we're going to go to see where it says calc in blue. That means hit the shift, calc, maximum 4. Put your cursor on the left side because it's asking for left bound. Hit enter, and then bring your cursor to the right side of the maximum. Hit enter, and then just place it anywhere in between and hit guess. It tells us 9.48 and 449.352. So I was 449.5 because of the rounding I did. If I would have rounded to the hundreds or thousands place, I would have gotten a more precise answer of 449.352 for the maximum profit. And that was part D. So this last problem is a regression problem. Table 6 gives the performance data for a boat powered by an even root outboard motor. It says use the quadratic regression to find the best model of the form y equals ax squared plus bx plus c for fuel consumption in miles per gallon as a function of speed. So when it says as a function of, that means that's your input or your independent. So speed is our independent, and they want fuel consumption to be our dependent. So we're using these two columns. This will be X and this will be Y. And when we plug this into our calculator, this will be list 1 and list 2, so we can use the regression feature. So we're going to type this into our calculator. We go to Stat, Edit, list 1. We'll type in the numbers from the mile per hour column. And now we hit the Stat button again, go over to the Calculate column, and go down to Quadratic Regression. Our X list is list 1, our Y list is list 2, those are correct. And we'll hit Calculate. So we see that we've got our A, B, and C values now, so we can say that our quadratic function is y equals negative 0.0097 x squared plus 0.507x minus 0.179. Now it says estimate the fuel consumption to 1 decimal place at a speed of 12 miles per hour. So we're going to find y of 12. So I've entered the quadratic equation into y1. I'm going to go to table set and tell the table I want to type in a specific independent value. So it will ask me. And when I go to table, I want to type in 12 for my x value, and it'll plug it into the function and tell me 4.5. 0.82. It says estimate fuel consumption to 1 decimal place, so 4.5 miles per gallon at 12 miles per hour. So this is the end of the lesson. So review the video, complete the note packet, complete your practice problems, and come to class with questions next week.